In this video, we'll talk about a popular model in deep learning, the deep autoencoder. So here we're considering the case where instead of training a single hidden layer autoencoder, we would actually want to train a multi-layer autoencoder. In particular, the autoencoder we'll be interested in is an autoencoder where the encoder gradually decreases the dimensionality of the input. So it extracts a 2000 hidden unit vector representation. So 2000, that's just an example. We could have chosen other numbers. But then we will gradually decrease the representation as we move along in the computations made by the encoder. And so this would allow us to reach eventually a very small dimensionality, even like a 2D representation, which we could, for instance, visualize as an image to do some data visualization. And then the decoder will not just be a single linear plus nonlinearity reconstruction operation. It will actually, again, gradually increase the dimensionality from the encoded representation into 500 like here, and then 1000 like here, and then eventually 2000 like here, and then ultimately go back into the input space and do a full reconstruction of the original input here. So training such a deep autoencoder is actually very hard, and in this case, the problem we face is not really overfitting, but more underfitting. It's actually hard to reach very good training error, especially if you have a large training sample. And turns out that if we use the pre-training with unsupervised learning procedure, where we greedily train, say, a first RBM and then a second RBM and so on. So actually this would be the first RBM, then get another RBM here, another RBM, and so on until we reach a hidden layer of 30 hidden units. If you use this to initialize a deep autoencoder, we actually get some quite good results. So this was a result presented by Jeff Hinton and Ruslan Salakudinov in Science in 2006. And that's somewhat surprising because I've argued thus far that pre-training with unsupervised learning was useful to obtain good regularization, so to fight overfitting. And here it seems we're actually fighting underfitting. So that's somewhat surprising. So this perhaps means that unsupervised pre-training doesn't play only a role of regularization, but perhaps it can be sometimes useful for improving the quality of the optimization. Here it could be due to the fact that we're actually not performing classification. We are doing unsupervised learning. Training a deep autoencoder is unsupervised learning. We're not predicting a label. We're really reconstructing the input. So perhaps there's a relationship between unsupervised pre-training and just doing better at global joint unsupervised learning. So that's perhaps part of the reason. But that being said, this is a procedure in the case of the deep autoencoder where unsupervised pre-training actually helps fighting underfitting. Also, better optimization algorithms will help. There's this paper, Deep Learning via Hessian-Free Optimization by James Martin in 2010 that showed that instead of using stochastic gradient descent, if you use more sophisticated second-order optimization, we could actually get really good result even without pre-training with unsupervised learning. So I'm mentioning this because this is a model, the deep autoencoder, which is often used for evaluating better optimization algorithms in the context of neural networks, in the context of deep learning. So one application for it is to reduce the dimensionality of some data set. If you wanted to, for instance, take these big images and actually store them in a much smaller dimensional vector so that we can actually store this on disk more easily. And then if we keep the decoder around, then we can easily reconstruct the original input. And if we compare that with the type of representation we would get if we did PCA, and then from PCA we provided the reconstruction, we see that the reconstruction we get is much better with the deep autoencoder than with PCA, where this is the original data. Notice that here, because we're talking about a deep autoencoder, so we showed that PCA was in some sense optimal compared to training a single hidden layer autoencoder with some nonlinearity. So essentially PCA will do better than any autoencoder with single hidden layer and the squared output reconstruction error. But because here in the deep autoencoder we have a nonlinear decoder, then essentially the demonstration for PCA being optimal does not apply for the case of a deep autoencoder. So a deep autoencoder could improve over PCA because it has a more complicated nonlinear decoder, multi-layers that sequentially reconstruct or increase the dimensionality until we reach the original input space. Okay, so this is why this result is not really a contradiction with respect to what we've seen before in the single layer autoencoder case. Another application is just visualization. So if we make the middle hidden layer a two-dimensional vector, then we can actually plot this by taking all of our data and placing a point in 2D at the position given by the two-dimensional vector. And so this is an example from, again, the same science paper where an autoencoder was trained on documents, where a document is represented by the frequency of each possible word, where each possible word that we can recognize in a document is a different dimension. So words are pixels, essentially, if we want to make a correspondence with images. And then the intensity of pixel is just how many times we see the given word in that document. And we see that it seems to learn to essentially put together documents that talk about similar things. So say disasters and accidents, legal, judicial, government borrowings, account earnings, and so on. So the color represents these different classes, and we see that they are close together in this 2D visualization of the original data. Okay. So that's a deep autoencoder. It can help us get a very small dimensional representation of some data that still maintains quite a bit the original information from the original data. It can help us with 2D dimensions, 2D visualization of the data. And there's quite a bit of research being done over these models because they're a good benchmark in particular for evaluating better optimization algorithms for neural networks.